Hello students, welcome to IMS GATE Academy. Myself Vijaya Kumar. I am going to give you second session of revision of manufacturing technology for GATE point of view. Okay. Thank you. Now let us move. And last session we have seen that so it's a part 2, guys. Last session we had been discussed about rolling. Okay, in metal forming process, rolling we had been discussed. Now let us go for watching that wire drawing operation. In the wire drawing operation, I will give you some important formulae. Wire drawing operation. Right. So in that wire drawing operation, I am going to give you some important formulas. So now let us understand that what is a wire drawing operation, how it is look like. So here in wire drawing operation, what happened now? A solid rod is drawn through two stationary dies such that rod is going to be converted into wire. Okay. So series of dies we use here. So now this is a one stationary die, okay, as we have discussed already. Now from here also it is a stationary die. So here it is a die. Right, guys. So two stationary dies are there. In between them, if you drawn this particular rod, it is going to be converted into wire after number of drawings. Okay, after number of drawings. So let me extend this for certain distance. Okay. Now here rod is going to be converted into wire. Rod is going to be converted into wire. Now initial diameter of the wire is Now let me give you guys. This is what initial diameter of the wire, D0 we say, and here final diameter of the wire we say that it is a DF. All right. Now some back tension may be applied, that is sigma naught, and front tension may be applied. Sometimes it is called, so front tension sigma 1 we call. Okay, right. Now here, so this is a deformation zone angle, or we can call it as a diangle. So here diangle is 2 alpha. Diangle we call 2 alpha. So this diangle may be varies from 12 degrees to 48 degrees. Okay. For hard materials it is 12 degrees. For soft material it is 48 degrees. Clear, everybody? Hope you understand. Okay. Now this is what about rod is going to be converted into wire, and this rod is going to be certain velocity, say that velocity V. With certain velocity, the rod is going to be drawn in between the two stationary dies such that what happened now, rod is going to be converted into wire. So during this process, what happened now, the stresses developed in this material is greater than yield stresses and less than ultimate stresses. So that what happened now, material experiences the plastic deformation for converting rod into wire. Okay, right. During wire drawing operation, stresses developed in the material, that means workpiece material, isn't it? Okay. So in material greater than yield stresses, and less than ultimate stresses. less than ultimate stresses. Okay. So here, so developed stresses sigma, if you consider, it is must be greater than yield stresses of material, must be less than ultimate stresses of material. Whenever material experiences these, in between these stresses, it is experiences the plastic deformation for converting one shape into other shape. It is a standard definition for metal forming process, isn't it, guys? Okay. Now let us calculate the drawing stress. How to calculate drawing stress and drawing load as well, right? D naught we consider it as a initial diameter of rod, initial dia of rod. Okay. Now where A naught is a cross section area of rod, cross section area of rod, cross section area of the rod. Okay. Now from here, how can we calculate A naught? A naught can be calculated. It is pi by 4 D naught square. All right, guys. Now similarly, DF, final diameter of the wire. Final diameter of wire. Final diameter of wire. Isn't it, guys? Now here AF, that is how can we calculate AF? That means cross section area of the wire. Cross section area of wire. Cross section area of wire. Yes, guys. Now this also can be calculated. AF is equal to, it is pi by 4 DF square. Obviously area in mm square, right, guys? So let me go for back to our diagram. So now this is what now see, this is what the cross section area of the wire, final wire, that is, here it is AF. Okay. Now here initial cross section area somewhere here, it is gonna be a naught, isn't it, guys? So how much percentage reduction is going to be percentage change in cross section area? Sometimes they may ask that see how much percentage cross section area is going to be decreased. Okay, right. Now let us go for percentage reduction in cross section area. Percentage reduction or percentage change. Percentage reduction in cross section area. That we can calculate, A naught minus AF by A naught into 100. So that you are going to get, it is a percentage change in cross section area. And also draft can be calculated here. Draft can be calculated here. So K we call, it is going to be A initial by A final is a draft in the drawing process. Okay, right. Now let us go for how to calculate drawing stress. How to calculate drawing stress. Let us see. Drawing stress. Drawing stress. So drawing stress here I am taking it as a sigma D. Drawing stress I am taking it as a sigma D. So how can we calculate sigma D? Sigma D is equal to, it is sigma F into, it is 1 plus B by B into, it is 1 minus AF by A naught whole to power B. Okay, up to here. Okay. Now here minus, it is AF by A naught whole power. Here it is a sigma naught if back tension is given. So if back tension is given, then only you just apply this formula. Otherwise, no need to, you just neglect this term if back tension is not given. Neglect this. Neglect if no back tension in drawing. No back tension in drawing. All right, guys. So now if I neglect that, my final formula will be, sigma D is equal to, it is sigma F into, it is 1 plus B by B into 1 minus, AF by A naught whole to power B. This is what your drawing stress. Okay. Now here sigma F is the flow stress of material. Sometimes yield stress also given. So you may take it as a yield stress or flow stress of material. Okay. All right, guys. Now sigma S is a flow stress of material. Flow stress of material, isn't it? Okay. Now let us calculate that B. So B is equal to, here it is a mu cot alpha. Okay, where mu is a coefficient of friction, between workpiece and die. Okay, right. During wire drawing operation, what happened? So the draw is going. So that is the workpiece is going in this direction. So that friction will act in this direction. So that is why the coefficient of friction between the die and rod is this one. Okay, mu. Right. That is what I wrote here. Right. Mu is a coefficient of friction. Now where is alpha? So 2 alpha is a diangle. 2 alpha is a diangle, where alpha is a half of diangle. Half of diangle. Half of diangle, isn't it, guys? Right. Now here I just wanted to highlight one thing, guys. Here 2 alpha varies from 12 degrees to 48 degrees. Okay. Now this 12 degrees for hard material drawing. Hard material. So if your workpiece material is very hard, then you use very small alpha. Okay. Now 48 degrees. If for soft materials drawing, this is soft material drawing, isn't it, guys? This is what happening, right? Now, so drawing stress we have calculated. Okay, drawing stress we have calculated. So drawing stress is equal to, if you apply this formula, as you know that AF is the final cross section area, A naught is the initial cross section area. So B is the mu cot alpha and alpha is the half of the diangle. Suppose a diangle is given 20 degrees, then you are supposed to take alpha is 10 degrees. Half of the diangle you are supposed to select. Hope you understand, guys. Now let us go for drawing force. How much force required for drawing? How much force required for drawing? Right. Next is drawing force. Drawing force. So we can say that it is a F we can call, or we can call it as a drawing load also. Okay, right. Now drawing force is equal to drawing stress into final cross section area. Okay. Similarly, so drawing power. Power required for drawing operation. So P is equal to, it is so drawing force or drawing load, drawing force or, oh my god, 1 minute, guys. Drawing force, oh god, drawing force or load multiply with drawing velocity. At what speed? Drawing velocity. Okay, right. From here, drawing force we have seen that F or drawing load and drawing velocity is a V. Okay, so now so that you are going to get power required in watts. The units here, watts you are going to get. Yes, guys, understood everybody? Hope you understand. Okay, right. Now let us move for what is the maximum reduction in drawing? Okay, suppose say that, guys, if I go for the back of the diagram, then what happened? So here some reduction is going to be takes place in the cross section area. So when we can get maximum reduction? When we get maximum reduction, suppose say that if you take this is a 30 mm and it is reduced to 5 mm. In that case, what happened? how much reduction, maximum reduction per pass for one pass. If you draw a rod in between the two stationary dies, how much amount of the maximum reduction is going to be takes place. So that condition I am going to explain you. Okay. So the maximum reduction is possible whenever the maximum reduction in drawing, the maximum reduction in drawing, the maximum reduction in drawing takes place when okay, drawing stress is divided by flow stress of material equal to 1. Okay, that means drawing stress equal to flow stress of material. In that case, maximum reduction is going to be takes place. Okay, so here you can write also when sigma d equal to sigma f, such that maximum reduction is going to be takes place. Clear everybody, guys? Now from here I can write my drawing stress equation. What is the drawing stress equation? Sigma d is equal to, it is sigma f into 1 plus b by b into, it is going to be a 1 minus af by a naught whole to power b, this much. Okay. Now for maximum reduction case, for maximum reduction case, for maximum reduction, sigma d divided by sigma f is equal to 1. Okay. Now for my, if I apply this, sigma f by sigma d is equal to 1, so that my equation is going to be become, oh my god, what happened? One minute, here only I'll write. My equation is going to become, so 1 plus b by b into 1 minus af by a naught whole to power b equal to 1. So this is what sigma f by sigma d equal to 1 na? That is why this is what the condition for maximum reduction case. Okay. So hope you understand everybody. Next, for ideal case of drawing, right. Now let us go for 1 minute, guys. For ideal case of drawing, what do you mean by ideal case? Ideal case of drawing. Yes, guys. What do you mean by ideal case? Then whenever friction is going to be 0, in that case we are considering it as a, we consider it as a ideal case of the drawing. Okay. So for ideal case of the drawing, coefficient of friction equal to 0. Okay. Now what happen if coefficient of friction equal to 0? Now let me explain you guys. Now see, suppose sigma d is equal to, it is sigma f into 1 plus b by b into, it is 1 minus af by a naught whole to power b. Okay. Now see, if mu equal to 0, then what happened to the b? Mu cot alpha. So if mu equal to 0, b equal to 0. If b equal to 0, then 1 by 0, 0. So it is 0, 1 minus 1. So this is into entire 0. So that for ideal case of the drawing, sigma d is equal to 0. But so in this case, for ideal case, for calculating the sigma d drawing stress, we have another formula. Okay, right. Now for ideal case of drawing, sigma d can be calculated. It is so it is going to be a sigma f or sigma y into ln of a naught by af. Okay, so this is for ideal case of the drawing. This is for ideal case of the drawing. For ideal case means b equal to 0. All right. Now one more thing here, only I will conclude that force in ideal case. Okay, so that is also sigma d you calculate by using this formula, and then you calculate the force for ideal. Okay, so right now let me write that force in ideal case of drawing. Force in ideal drawing, that is F is equal to drawing load, that is drawing stress for ideal into it is AF. Okay, so drawing stress ideal, so that you can multiply with that. So hope you understand, everybody, guys. Right, have a look on this drawing once, and then we'll go for the next concept. Right, now let us go for extrusion. Now let us go for extrusion. Extrusion. Okay, guys, so now let me give you extrusion process. Extrusion process. What is extrusion? Actually, it is a extension of another metal forming process. It is another metal forming process in which what happened, it is an extension of the drawing process. It is an extension of drawing process in which the forces are applied backside of the material such that material experiences the compressive stresses. So whenever material experiences the compressive stresses, that are going to be equal to flow stresses, so that any amount of deformation can be possible. That is whatever the limitation we have seen in the drawing, that is a limited reduction as well as the load has to be applied for a long time for converting the elastic deformation into plastic deformation. That is the reason why here we have some limitations in the drawing operation, where in extrusion process what happened, so if you apply the forces from the backside of the material, so that stresses induced in the material is flow stresses, so that any amount of the deformation can be possible. So highest amount of the reduction is going to be takes place, and also no need to maintain the load for long time for converting the elastic deformation into plastic deformation. Clear, everybody? Hope you understand. Okay, now let me explain you with the help of diagram what is extrusion process. Now here it is a closed container, or we can call it as a billet. So now it is a ram, and through this ram we apply raw material over here. So here we will place the raw material here. Okay, we will place raw material here such that it is going to be deformed plastically like this, so that long bars, T sections, I sections, channels are going to be produced with this process. All right, guys. Okay, right. Now here it is a extrusion process. Now let me give you a small pointers as well. Okay, this is a container, closed container. Okay, now this is extruded product component, we call component, extruded component, right? Here it is a raw material placed inside the billet. Okay, so now I just hash this portion. All right, guys. Okay. Now, in this case, what happened? This is a billet material, and it's a initial diameter. Here, I'll show you that it is a D0. Okay. Now, it is a final diameter of the channel, that is a DF. Okay. So, it is a extruded component diameter. Extruded component diameter. All right, guys. Now, here, say it is a initial length of a workpiece. And now, here it is a final length of the workpiece. Right. Here, I would like to highlight one thing, guys. The D0 is very greater than DF. Okay. Now, here LF is very greater than L0. That means initial diameter is very high and final diameter is very less. We cannot compare that. That much amount of the reduction is going to be takes place in the extrusion process. Similarly, initial length of the workpiece is very less and final length of the workpiece is very long. So, sometimes there is a possibility that because of the very long length of this object, so there is a possibility that sometimes it may bend like this due to its self weight. So, to avoid that, we are using some rollers in order to maintain the block without bending. Okay. Right. So, these are the rollers which are used for to avoid the bending of the component. Okay. Right. Now, here, so let us go for some calculations over here. Okay. Now, so A0 initial. So, let me change my ink. Now, initial, it is equal to, it is so pi by 4 D0 square. Okay. That is initial cross section of billet or workpiece material. Initial cross section of billet. Initial cross section of billet. All right. Next, AF is pi by 4 DF square. That is equal to, here it is a final cross section of workpiece, component. Okay. Now, percentage change in cross section area. Percentage change in cross section area. Percentage change in cross section area. Percentage change in cross section area can be calculated by using, it is a A0 minus AF by A0 into 100. So that you are going to get it is a percentage change in cross section. Okay, guys. Right. Next, draft can be calculated here also. Draft that is indicate with K, that is equal to, it is A0 by AF. So, normally it varies from 40 to 50 general. Okay, it is generally 40 to 50. So, for up to 400 for very soft material. Very soft material, isn't it, guys? Very soft material, it is up to 400. Okay, right. Now, let us go for calculating the, but as we know that one thing we know that, see, in every metal forming process, we assume that material incompressible. That means change in volume equal to 0. That means whatever the volume is going to be undergone for metal forming process, the same volume is going to be existed. That is here volume is going to be constant in metal forming process, isn't it, guys? Now for volume constant means here it is a cross section area into length, we'll get volume. That means volume before extrusion equal to volume after extrusion. In simple words, no change in volume means whatever the volume before the extrusion of workpiece material, the same volume is going to be happen at the after extrusion as a component, isn't it, guys? That is the reason why here I'll write it as in extrusion in extrusion volume is constant. Volume constant. Not only extrusion, wire drawing, rolling and forging and other metal forming process also, volume is going to be constant. Suppose say that I'll write my volume, okay, right. Volume before forging, extrusion. Volume before extrusion is equal to volume after extrusion. Volume after extrusion. Volume after extrusion, right? Right. Now here, how can we write volume before extrusion, volume after extrusion, right? Now here, A naught into L naught is equal to here AF into LF, isn't it, guys? Yes, right. Now here I'll write this pi by 4 d naught square. So here d naught square into L naught is equal to df square into LF. Why? Because pi by 4 will get cancelled both sides. That is why I can write my relation. So d naught square is divided by LF. Oh my God, not df square. D naught square minus df square is equal to, it is going to be a 1 minute. LF by L naught. LF by L naught. This is a one relation in extrusion. Yes, guys. Okay. Now here, if you go for extrusion, certain velocity it is having before forging operation V naught. That means for piece, now it is a final velocity. So which one is greater? So which one is greater? That we are supposed to calculate, isn't it, guys? Okay. Now for that, volume flow rate before forging equal to volume flow rate after, so not forging, extrusion. Now I'll go for this. Volume flow rate before extrusion, is equal to volume flow rate after extrusion. Volume flow rate after extrusion. Volume flow rate before extrusion is equal to volume flow rate after extrusion. So yeah, good afternoon, Nazir. Nisar, okay, good afternoon. Okay, right. Now here, how can we write volume flow rate? Right. Let me write that volume flow rate. That is A initial into V naught is equal to here A final into V final, isn't it, guys? Right. So here what happened? So mm square, mm per second. So that mm cube per second. If you see, this is mm square and this is mm per second. Now mm cube per second. Now here also mm square into mm per second. So that mm cube per second. Here what I am trying to tell you, so units are also balanced. That means how much amount of the flow of molten workpiece material is entering into the die, the same amount of the workpiece material is existing from the die. So that is why volume flow rate is constant. Now I would like to highlight that which velocity is greater. Either initial velocity of the extrusion is greater or final velocity of the extrusion is greater. That is what we are supposed to decide. Okay. Now if you observe that small analysis, that is, I'll write this fellow. it is d naught square into V naught is equal to here df square into Vf. Yes guys, right. As I said that d naught is very greater than df. That means this is large. This is large. Now, so this is going to be less. So to balance this equation, if d naught square is large and df square is less, then obviously V naught is less and Vf is more. Okay. If it is more, if it is more and it is less, okay, and it is less and it is more, that is what I would like to highlight. So to balance this equation, if it is more, if it is this is less, okay, initial diameter is very large, final diameter is very less. In that case, to balance this equation, obviously final velocity of the workpiece meter, final velocity of the extruded component is more than that of the initial velocity. Okay, so by using this, I can write this. Okay, so that I'll write it is so so Vf is greater than V naught. Okay, so this is what another relation. Hope you understand, guys. Done. Right. Now let us go for stress analysis in extrusion. Stress analysis in extrusion. Stress analysis in extrusion. Stress analysis in extrusion. Now let me give you extrusion stress as well. Okay, right. Now extrusion stress. Extrusion stress sigma d is equal to it is going to be a, again it is a flow stress of material and it is going to be a 1 plus B by B into, so AF 1 minus AF by A naught whole to power B. Yes guys. All right. Now from here, so this is what the drawing stress. Okay. Now, so let me give you what is that B equal to, again it is going to be a mu cot alpha, where alpha is a half of diangle, and then mu is a coefficient of friction. All right, mu is the coefficient of friction. Now, where sigma F is a flow stress of workpiece material. Flow stress of workpiece. Yes, guys. Okay. So this is what about the what is that extrusion. All right. Now, so if they ask you to calculate, if they ask you to calculate, okay. Now, what is the stress required for extrusion? Then the stress developed in the extrusion, then you can use that formula, that is sigma F into 1 plus B by B into 1 minus AF by A naught whole to power B, where sigma F is the yield stress of material or flow stress of material, that will be mentioned in the problem. Okay. Now, they will give you D naught and DF final, and then you have supposed to calculate the extrusion stress like this. As you know that this will be given in the problem, and if coefficient of friction and diangle is given, so that you can calculate B and substitute all these values here, so that you are going to get extrusion stress. Yes guys. Okay. Now let us move for force required for extrusion. Right. Force required for extrusion. Force required for extrusion. Okay, right. So here EF is a extrusion force. So for forward extrusion, forward extrusion, it is going to be a sigma d into a naught here, not af, a naught here. So why? Because so here the force is applied from the back side. That is why initial cross section must be multiplied with the extrusion stress, so that you are going to get extrusion force. Okay. Now for extrusion force for backward extrusion. For backward extrusion, we require some additional force into it is A naught, where P is a pressure required for or force required for overcoming friction. I'm sorry guys, here it is a backward here and forward. In backward in forward only friction is more. Okay. Force required for EF, what is that? It is for backward extrusion and it is for forward extrusion. Okay. In forward extrusion, friction will be more because the raw material is moving against the container walls. That is why friction is going to be generated. Whereas in case of backward extrusion, what happened now? In backward extrusion, the raw material directly deformed from through the die, and it is not going to be travel against the cylinder walls. That is the reason why here what happened now? We are supposed to select excessive pressure for the ram in order to do the forward extrusion. Whereas in backward extrusion, no friction is there. That is why we can easily simply extrude the component. Okay. For maximum reduction. Right. For maximum reduction, in extrusion, okay, so mu should be equal to 0. If mu equal to 0, then B equal to 0. In that case, extrusion stress can be calculated, it is K into ln of, it is going to be A naught by AF. Okay, for maximum reduction case, okay, where K is a yield strength or flow stress of material. Yield stress or flow stress of material. All right, now extrusion force for ideal. Extrusion force for ideal. Extrusion force for ideal. So that is equal to, I can write it is K into A naught into ln of, A naught by AF. So by using this, we can calculate the force required for ideal condition of the drawing process. Hope you understand, guys. Done. This is about drawing. Next is, let us move for forging operation. Forging operation. So what happened in forging operation? Actually, forging operation is nothing but, it is the oldest metal forming process in which what happened, force is applied on the raw material under the heat or else without heat also. Forces applied on the raw material such that stresses induced in the material greater than yield stress and less than ultimate stresses, so that material experiences the plastic deformation for converting one shape to another shape is come under forging operation. But here I would like to convey one thing, guys. While you are applying the forces on the raw material, that forces or that loads may be continuous loads or maybe impact loads can be used. Okay. Now, in simple words, without removing any material from the work surface, if you apply forces and heat for converting the raw material from one shape to another shape is come under forging operation, right. Suppose say that if I take one material and with application of force and heat, if I am able to convert into another shape without removing any volume from the job, then it is considered as a forging operation. So in that case, I am just highlighting that whatever the forces you are applying on the body, that forces may be continuous force or impact loads. That means sudden loads. Right. Now here I am taking one particular job here. Okay. Now here two dies are there. So one is a fixed die. This is one is a fixed die. That means it is not going to be moved. Okay, fixed die, and it is going to be a movable die. All right, guys. Now here in between the two dies, the workpiece is placed. This is a workpiece, and its initial height is, say that, h0. Initial height is h0, and here its initial diameter is d0. Okay. Now here whenever I allow the movable die to down, such that what happen now, so the workpiece material is going to be plastically deformed and its diameter is going to be increased. Right. Now let me suppose give you that my movable die reached up to here. Okay, right. In that case, what happened? My job just expand like this, isn't it, guys? Now here it is gonna be a df and it is gonna be a hf. Isn't it, guys? Okay, right. Now here see, initially it is having certain diameter and certain height. After I allow the movable die to down such that it plastically deform, see, just now I am telling you here we just increasing the diameter and reducing the length through this process, okay, without removing any material from the work surface, isn't it, guys? Now my point is, what I am trying to highlight here, guys, here the movable die is moving continuously. That means continuous forces may be applied, or else the movable die may be applied some impact loads as well. So that loads depends upon your application of the force. Okay, right. Now let us go for, so in forging operation also volume is constant now. In forging operation also volume is constant, right? Now let me go for that. Meanwhile, I'll write it is some terminology here, right? Volume before forging is equal to volume before forging is equal to, it is going to be a volume after forging. Isn't it, guys? Volume before forging equal to volume after forging. Now how can we calculate volume before forging equal to volume after forging? That is equal to, it is A0 into H0 is a volume. That means cross section area of the block into its height, so that I'll get volume. Now similarly, volume for initial final cross section area into final height. So here I just replace my, this fellow is d0 square into h0 is equal to here df square into hf. Okay, so from here if I want d0, then I can write it is df into under root, you know, hf by h0. Right. Now again we also write this relation. If I want h0, here only I'll write h0 is equal to, here how can I write this fellow? It is d0 by, oh my god, not d0, df. df by d naught whole square into hf. So like that also we can write our formula, isn't it guys? Done, right? This is what the analysis of next. Here they may ask that the percentage change in diameter, percentage change in diameter. Okay, right. Now let's calculate that. Here percentage change in diameter in forging, percentage change in diameter. Okay, that is equal to, here d initial minus d final is divided by d initial into 100. Yes guys, right? Right. Now here force required for forging, force required for forging, force required for forging. Okay, now so that we can call it as F actual. F actual, that is equal to F actual is equal to sigma average into A final into Ks, into Ks. By using this formula we can calculate, sorry, here it is a initial cross section, it is a initial cross section area. So sigma average stress into area of cross section initial and then Ks. Okay, now here Ks is a friction factor, it is a friction factor. Okay, right. Now let me write all these formulas. Where Ks is a friction factor. Okay, it is always greater than or equal to 1. Okay, if it is friction is not given, then you can take that K is equal to 1. Okay, now otherwise you are supposed to calculate your Ks. Ks equal to, it is 1 plus 2 mu Rf is divided by 3 Hf. Okay, 2 mu Rf by 3 Hf. So now Rf is equal to, it is Rf is equal to, it is final diameter by 2. So that you are going to get Rf. Okay, so now this is how you are supposed to calculate your Ks factor. Okay, now force required for forging is equal to, this is what the formula, right? Now here Ks is equal to, it is gonna be this much, 2 mu Rf by 3 Hf. Clear everybody? Right, where mu is a coefficient of friction. Okay, now how to calculate? Sometimes sigma average mentioned in the problem itself, sometimes sigma average mentioned in the problem itself, but sometimes we are supposed to calculate average. So whenever strength factor is given and strain hardening component is given, strain hardening exponent is given, then you are supposed to calculate your sigma average. How to calculate sigma average? Please let me know. Let me explain you. Sigma average, we can write it as, it is K into epsilon F whole power n is divided by n plus 1. Okay, now let me explain the terminology here. Where okay, so n is a strain hardening exponent, strain hardening exponent, and here it is a sigma F is a true strain. So by using true strain, how can we calculate true strain? It is EF is equal to, it is ln of it is df by d naught, df by d naught. True strain can be calculated where K is a strength factor, Like that you are supposed to calculate your sigma average. Sometimes it is mentioned in the problem, sometimes we are supposed to calculate in the problem. So whenever n and k value is given, and you are supposed to calculate your sigma average. Okay. So hope you understand all, guys. Right. Now after finding the average, then you keep it here and calculate ks, and then a naught you know na, so then you substitute here, so that you are going to get it is a force required for forging operation. F actual is equal to this much. Hope you understand all. Yes, guys. Finished now? So have a look on this once. Forging. Stress is the extrusion, na? Right. Now let us go for forging. This is how forging. Right. So stay tuned, guys. I'll be back in a minute. I'll be back in 5 minutes, and we will start the metal cutting and machine tool operations. All right. Yes. Okay. Welcome, guys. Now let us shift our talk onto metal cutting. Shift our talk onto metal cutting. Shift our talk onto metal cutting. Okay. So in that metal cutting, so the first and foremost thing I would like to highlight that they may ask you to calculate that some formula I just repeat. Okay, some formula I just repeat. Okay, so they may ask you to calculate that average surface finish, average roughness, surface finish, surface finish. Okay, so that means average roughness is equal to average roughness RT is equal to, it is gonna be a, so F square by 8R. Okay, so where F is a feed that is mm per revolution. Okay, now where R is a nose radius, R is a nose radius. Okay, now so this is RT value. Once you calculate with the help of feed and nose radius, so that you are going to get some average value. Based on that average value, you can decide that whether surface is roughness or is a smooth one. Okay, right. Now the surface roughness can also be calculated by using the formula that if side cutting edge angle, end cutting edge angle is given. If side cutting edge angle, end cutting edge angle is given, we can calculate like this also. F is divided by tan CS plus cot CA. Tan CS plus cot CA. Okay. Now let me write here also average roughness, and let me write some terminologies here. Now here again F is equal to, it is a feed, that is mm per revolution. Okay. Now where CS is a side cutting edge angle, side cutting edge angle, side cutting edge angle. Okay. Now here CE is the end cutting edge angle, end cutting edge angle, end cutting edge angle, isn't it, guys? Okay. By using this also we can find out the surface roughness. Okay. Now let us go for analysis of orthogonal machining. Analysis of orthogonal machining. 1 minute. Analysis of orthogonal machining. Orthogonal machining. Analysis of orthogonal machining. Right. Now here we have two actually, oblique machining and orthogonal machining. What is orthogonal machining? Now let me explain you. Orthogonal machining is nothing but, if the cutting edge of the tool is perpendicular to the cutting axis or cutting velocity vector, then it is considered as a orthogonal cutting. Okay. Now if the cutting edge of the tool is not perpendicular and it is certain angle to the cutting velocity vector, then it is considered as a oblique cutting. But we are not required for oblique cutting, and we just go for orthogonal cutting operation, orthogonal analysis, because in orthogonal only most of the problems will come from the gate point of view. Okay. Now let me go for that. So with the help of diagram, I just used to draw this. right. Right, this is tool and this is a chip and here it is a workpiece. Yes guys, okay. Now let me give you some terminologies here. Here it is a T1, that is a uncut chip thickness. Now here it is a T2 cut chip thickness. Okay. So before cutting operation, what is a chip thickness? After cutting operation, what is a chip thickness? Now here this fellow is a uncut chip length, that is L1. Now this is a cut chip length L2. Okay. Now here if you observe that B1 also there. So not require this B1. Right. Now similarly along with this shear velocity will, so here shearing is going to be takes place, that is why it is called shear velocity Vs, and chip flow velocity we call it as Vf. Chip flow velocity we call it as Vf. Okay. Now let us go for, cutting velocity will come in this direction, cutting velocity Vc. Now this angle we call it as a shear plane angle. Okay. So the shear plane which is make an angle to the horizontal plane or to the cutting axis, then it is considered as a shear plane angle. Now apart from all this, rectangle is there. This is your rectangle alpha. This is your rectangle alpha. Hope you understand guys. Okay, right. Now let us write some terminologies and then we will move forward in this. Okay, right. Right. T1 is uncut chip thickness. Uncut chip thickness. Okay. Now T2 is cut chip thickness. T2 is cut chip thickness. Okay. Now L1 is a uncut chip length. Uncut chip length. Right. Now L2 is a cut chip length. Cut chip length. All right, guys. Right. Now again, B1 is a uncut chip width. Uncut chip width. And B2 is a cut chip width. Cut chip width. Fine guys. Okay. Now from here, so T1 by T2 we call it as R. So chip thickness ratio, where R is called chip thickness ratio. R is equal to, it is chip thickness ratio, isn't it guys? So where R is equal to chip thickness ratio. Right here, actually in machining operation also we consider it as a volume is going to be constant. Okay. So volume of metal before machining equal to volume of metal after machining. Okay. 1 minute guys. right. Now let me give you volume before machining equal to volume after machining. Volume before machining is equal to volume after machining. Volume before machining equal to volume after machining. Then how can we calculate that? Volume before machining equal to volume after machining. Now let me go for that. That is T1 into B1 into L1 is equal to, it is T2 into B2 into L2. So here B1 equal to B2 in machining. So that is why here we can get the T1 into L1 is equal to, it is T2 into L2. So that I can write my equation T1 by T2 is equal to, it is L2 by L1, that is equal to R. That is equal to R. This is a one relation, isn't it, guys? Okay. Now one more thing, that is volume flow rate before machining equal to volume flow rate after machining. Volume flow rate before machining, volume flow rate before machining is equal to volume flow rate after machining. Volume flow rate after machining. Yes, guys. Volume flow rate before machining equal to volume flow rate after machining. So that here what happened now? Let me write that volume flow rate, that is T1 into B1 into Vc is equal to, so T2 into B2 into Vf. Okay, right. Now if I go back to this one, see volume flow rate Vc into T1 into B before machining, volume flow rate Vf into T2 into B, isn't it, guys? Right. Now right, let me go for this. Now here B1 is equal to B2, such that it is going to be a T1 into Vc is equal to, it is T2 into Vf. So that what happened? How can we conclude that? So T1 by T2 is equal to, so Vf by Vc, that is equal to R. Another relation in another relation. This is a second relation, right? Yes, guys. Okay. Now here I would like to add few more things here. That is alpha is a rectangle. Alpha is a rectangle. Now not theta. Phi is a shear plane angle. Shear plane angle. Okay, right. Now again let us write. Now velocities in machining zone. Velocities in machining zone. Velocities in machining zone. Yes, guys. Right. What velocities are going to be act in the machining zone? So as I said that, so Vc is a cutting velocity, isn't it, guys? Vc is a cutting velocity. Cutting velocity, and or we can also call it as, velocity of tool relative to workpiece. Velocity of tool relative to workpiece. Relative to workpiece. Here only we will conclude. Velocity of the tool relative to workpiece. Okay. Next, Vs. Here shear velocity. Shear velocity, or we can also call it as, velocity of chip relative to workpiece. Velocity of chip relative to workpiece. relative to workpiece. Yes guys, right. Next we have shear flow velocity. Not shear flow velocity, here it is a chip flow velocity guys. Chip flow velocity. Chip flow velocity or velocity of chip relative to tool. Velocity of chip relative to tool. Velocity of chip relative to tool. Okay. Now let us go for C. If I take a simple diagram, right, as you know that it is a chip and it is a workpiece. Okay, right. Workpiece, tool, and then chip. Workpiece, tool, and then chip. Yes, guys. Velocity, chip, and tool, isn't it? As we have discussed that, okay. Cutting velocity and shear velocity and chip flow velocity VF. Okay. Now cutting velocity, that means tool is moving relative to workpiece in this direction, shear is going to be takes in this direction, and chip flow, that means chip velocity on the tool surface is going to be takes place like this, isn't it guys? Now here what I am going to conclude here, see, suppose if I take the velocity vectors this is our phi and this is our alpha, right? Now if I take the diagram of the velocity vector, so cutting velocity vector VC is going to be in this direction. Okay. Now, so if I take that chip shear velocity is going to, sorry, chip flow velocity is going to be in this direction. Now shear velocity is going to be in this direction. That means if I'm able to extend all these so that they are going to be form a triangle. See this here, if I go in this and this fellow if I draw like this and this fellow if I draw like this, they are going to be form a triangle. That is what I have drawn here. Now if I take perpendicular here, then it is going to be a alpha. This is alpha. Next, this fellow is phi. If it is this alpha, this fellow is 90 minus alpha. 90 minus alpha. Yes, guys. Right. Now, this is going to be a, and this angle is 90 minus phi minus alpha. So, apply sine rule here. If I apply sine rule here, what I am going to get? If I apply sine rule here, what I am going to get here? So, opposite this VC is divided by opposite angle of sine. That is, VC is divided by sine of 90 minus phi minus alpha is equal to, here it is, Vs is divided by sine 90 minus alpha. Okay. Next, Vf is divided by sine phi. Right. If I simplify this equation, then I am going to get it is Vc is divided by cos phi minus alpha is equal to, it is going to be a Vs is divided by, so cos alpha, and then Vf is equal to, it is going to be a sin phi. Okay, this is what the relation, velocity relation in the merchant circle. Isn't it, guys? Done. Right. Now let us go for forces in machining zone. Forces in machining zone. Next is forces in machining zone. forces in machining zone. Forces in machining zone. How many forces are going to be acting in the machining zone? Okay. So, during machining operation, what are the forces are going to be act in the machining zone? That is what we would like to highlight. Okay. Now, suppose say that I'll take one diagram here, guys. Right. Now, as you know that it is a chip and it is a tool, right? Say that it's a workpiece and tool and then chip. Yes, guys. Right. Now, let me go for C. Here, the tool force, that means cutting force is acting in this direction. FC is a cutting force. So, from the tool, the cutting force acting in this direction. Exactly perpendicular to this fellow, thrust force is going to be act, FT, right. Now, here it is going to be a friction force. So, when chip is moving in this direction, tool moving in this direction, so that so friction is going to be act downward like this, friction force, right. Now, normal to friction, normal force is going to be act. Okay. Now, so exactly on the shear plane, shear force is going to be act, Fs. Now, normal to shear force to normal, Fsn is going to be act. So, there are total 6 forces are going to be act in the machining zone. Okay. What is that? Cutting force, thrust force. Now, let me write that. Now, Fc is a cutting force. Now, Ft is a thrust force. Ft is a thrust force. Next is, Fs is a shear force. Fs is a shear force and Fsn is a normal to shear force. Normal to shear force. Okay. Next is F is a friction force. F is a friction force and N is a normal to friction. Normal to friction. Normal to friction. Yes, guys, understood? So, but here what happened now, guys? So, if I want to calculate the power required for the machining operation, that means how much power required for my machine tool to remove this amount of the chip. So, in order to get the power, I know that cutting velocity, right? So, cutting velocity into cutting force, so that I am going to get power required for the machining. But the thing is here, if I am able to solve these all forces magnitude, then only I can get resultant force over there. If I am going to get the resultant force magnitude, so that I can able to calculate the power required for the machining operation. For that purpose here, but the thing is here, these two are the measurable forces. What are that? Cutting force and thrust force, by keeping the dynamometer from, on the machine table, so that we can measure the cutting force as well as the thrust force. But we cannot measure that shear force, normal to shear force, friction force and normal to friction force we cannot be calculated. Why? Because they are acting in the dynamic zone. They are acting in the dynamic zone. So that here only 2 measurable forces, there are 4 non-measurable forces. Then how can we dissolve this? How can we resolve this particular concept? Okay, right. For that purpose, merchant is a scientist who establish a relation between the measurable forces and non-measurable forces in order to evaluate and find out the magnitude of all these forces. So that is what we call it as a merchant circle. Merchant circle is a thing which establish a relation between the measurable and non-measurable forces, so that if you know any two forces and angles of shear plane angle and friction angle and also rake angle, so that it is possible to find out the all the forces. Okay, now let us go for merchant circle. So it is a very, very important, guys. You will get definitely a question from merchant circle, right? Now let me draw this merchant circle. Merchant circle. All right, merchant circle. Right. Now it is a very important. Draw a circle. Better I'll go for some shapes. If you able to if you are able to understand the merchant circle, so that it is possible to find out one minute, guys. Right. Now here I am taking that. Now tool is going to be contact with the workpiece here. Right. Now let me draw the forces. Right. Now where is the cutting force? Where is cutting force? Cutting force is going to be act in this direction, isn't it, guys? So it is a cutting force, right? Now thrust force is acting perpendicular to the cutting force, so it is a cutting thrust force, right? Now here friction force acting downward, so now here friction force is going to be acting downwards like this. Okay, normal force perpendicular to this is a normal force. This is your normal force. Next, shear force. Shear force acting along shear plane. This is your Fs. Now normal to shear force, it is this one, Fsn. Okay. Now let us decide that angles. Now the resultant of all these, is going to be act in this direction. Okay. Now here it is a resultant. Now let's decide the angles. As you know that if I draw like this, then this is my alpha, isn't it, guys? Okay. Now this is your phi. Okay, right. Next is here it is a beta. Okay, this is 90 degrees, this is 90 degrees and this is also 90 degrees. Okay. Now this gonna become 90 minus beta. Now if I calculate this, this becomes beta minus alpha, this angle. Clear everybody? So in this manner you are supposed to draw your merchant circle. Okay. Now so from here I just see, from here I just draw the some I'll give some names over here. O, A, B, C and D. O, A, B, C and D. Okay, right. Now from triangle, so what is this total angle, guys? So first we'll take triangle OBC. From triangle OBC. So from triangle OBC. So cos of beta minus alpha. Cos of beta minus alpha, that is equal to, how can we write that, is cos OB by OC. OB by OC. As you know that what is OB? It is a FC is divided by R. Okay. Now I can write my R is equal to, it is a FC by cos of beta minus alpha. Okay. Say it is equation number 1. Right. Similarly, sin of beta minus alpha. Sin of beta minus alpha, that is equal to here BC by OC. BC by OC. Now here BC is FSN, right? Sorry, FT. FT is divided by R. Again, I can write my R is equal to, here it is FT is divided by sin of beta minus alpha, isn't it? Say that it is equation number 2. Alright guys, here it is. Here it is, Ft is divided by sin of beta minus alpha and it is a second equation R. Now see, by using this OBC triangle, I found that sin of beta minus alpha, cos of beta minus alpha. Similarly, you take that OCD triangle. So OCD triangle, from triangle OCD. From triangle OCD. Now similarly, what is that? Triangle OCD, and you take that cos of beta minus alpha, sorry, cos of beta and cos sin of beta. Okay, right. Now cos beta will take first. Cos beta is equal to, how can we write cos? So it is CD divided by OC. CD divided by OC, isn't it guys? Now what is CD? CD is N and OC is R, such that my R is equal to, it is N cos beta. So it is again equation number 3 you say. Okay, right. Next, sin beta in the same triangle. Sin beta is equal to, it is OD divided by OC. It is OD divided by OC. Now my OD is F and my OC is R. Okay, such that again I'll write my R is equal to F by sin beta. Say it is equation number 4. Say it is equation number 4. Okay. Now let us go for triangle OAC. Triangle OAC. Triangle OAC. Now from triangle OAC you are supposed to calculate total angle. What is this total angle? Phi plus beta minus alpha. So cos of phi plus beta minus alpha and sin of phi plus beta minus alpha. You are supposed to write like that. Okay, right. Now from triangle OAC. Here only we will finish. From triangle OAC is equal to, it is first we will calculate cos of beta minus alpha plus phi. It is gonna be a cos of beta minus alpha plus phi. Cos of beta minus alpha plus phi. OA by OC. OA by OC. OA by OC. Now here OA is Fs. Okay. Now here cos of beta minus alpha plus phi, OA is equal to, it is Fs is divided by R. Okay. From there I can write my R is equal to Fs is divided by cos of beta minus alpha plus phi. Yes guys, say that it is equation number 5. Okay, right. Next, similarly, sine of beta minus alpha plus phi, such that it is going to be a AC is divided by OC. AC is divided by OC, right? Now from here, sine of beta minus alpha plus phi is equal to AC is FSN is divided by R. Okay. Right. See, it is equation number 6. Guys, if you properly observe that, so all the equations 1, 2, 3, 4, 5, 6 equation I wrote in terms of R. Okay. Now, if you know that any two forces and angles of rake angle, friction angle and shear plane angle, if you know that, so that it is possible to find out any kind of force. Here, hope you understand, guys. Okay. Now, let us see that. Suppose say that I'll take equation number 1. I'll take equation number 1 and equation number 5. Okay. Both are equal to R, na? Equation number 1 and equation number 5. From equation number 1 and 5, I can write it as FC is divided by, cos of beta minus alpha is equal to Fs is divided by cos of beta minus alpha plus phi is equal to R. Isn't it, guys? Right? If I know FC, if I know these three angles, so that it is possible to find out FC. Okay, FC, FR I can find easily. Okay. Similarly, you can equate any equation. Because all the equations I have derived in terms of R. So suppose say that from equation number 3 and equation number 6, then what happened? N by cos beta is equal to Fsn by sine of beta minus alpha plus phi you can write. So if you able to draw the merchant circle properly, so that you can derive your own equation in your own style. Clear, everybody? Right. Now let us go for how to calculate phi, shear plane angle. I'll give you the formula for this. Shear plane angle. Okay, that is equal to phi. So that we can write it as, shear plane angle is equal to, that is tan phi is equal to R cos alpha by 1 minus R sin alpha. R cos alpha is divided by 1 minus R sin alpha. Isn't it, guys? Right. Now from here, it is going to be like this. Right. So R cos alpha by 1 minus R sin alpha. Now similarly, how can we find the beta? So as we know that, see, in this triangle OBC, so find out that tan beta minus alpha, right? As we know that tan beta is equal to mu, right? How can we find out beta? So here I can write it as beta is equal to tan inverse mu. All right. So like that we can calculate. Let us go for, so from triangle, what is that? I forgot. Triangle OBC. Right. From triangle OBC. Okay. Now tan of beta minus alpha is equal to, it is going to be a FT by FC directly I am writing. Okay. Now we just go back and check this once. So tan of beta minus alpha is equal to FT by FC I wrote. Right. Now here, from here, how can I write? My beta minus alpha is equal to, it is tan inverse FT by FC. Now my beta is equal to, it is alpha plus tan inverse of, FT is divided by FC I can write. Yes, guys. So from here I can get beta. Once I get beta and alpha and phi, so that I can find any kind of things. Hope you understand, guys. So have a look on this once. Right. Now let us go for, if shear force is acting in the machining zone, shear strength also develop na. Suppose say that shear force is acting over here, right? Shear force is acting on here. Okay. Now, so that shear strength is going to be developed. Okay. Now let us calculate that shear strength in machining zone. Shear strength in machining zone. Shear strength tau we call. Now, how can we write our shear strength? Shear strength is equal to tau is equal to shear force is divided by, let me write in terms of shear force is divided by shear area. Shear force is divided by shear area. Yes, guys, right? Now, from here, I can write in terms of formula, and shear force is divided by Fs, and shear area we consider it as a As. Okay. Now, where shear area is going to be happen? Now, let me show you that. This is right. Now, right. So, can I say that this is my shear plane? Can I say that this is my shear plane? Right, shear plane. Now, so whatever the area is here, that is a shear plane area, As, isn't it, guys? Right. Now, say that if I want that this is my B, this is my B. Now, say that this is a L0. Say this is a L0. Right. Now, here it is a shear plane angle phi. Shear plane angle phi. Right. Now, here shear area. Shear area. Can I write it is L0 into B? Can I write it is L0 into B? Yes, guys. L0 into B is a shear plane area, isn't it? Right. From here, see, L0 into B I wrote. Now, we don't know L0, B we know. So, how can we calculate L0? So, for that you take this angle, you take this angle. So, in this angle, what is this? This is a T1, na? This is a T1. Now, here in this triangle, take that sin phi. Sin phi is equal to, how can we write sin phi is equal to, it is going to be a T1 by L0, T1 by L0. Now, I require L0 shear plane length, that is going to be a T1 by sin phi I am going to get here. Yes, guys, done. Now, as I know that L0 I know and B I know. So, let us substitute here. Shear force is divided by As is a L0 into B. Okay, now let me write my L0 value also. L0 is equal to T1 by sin phi na. Fs is divided by T1 by sin phi into B, right. So, from here I will write my final formula of shear stress, Fs into sin phi is divided by T1 into B. So, this is what my shear stress formula. Okay. So, to avoid mixing of this is how I will draw, right. Nothing is there, guys. It's a very simple. It's a very simple. See that here shear plane, this is the area. That area will get L0 into B. Now, L0, we don't know the L0. So, for finding L0, I have taken this triangle. So, from this triangle, sin phi is equal to T1 by L0. So, this is L0, this is also L0 na, right. From there, so I find my L0. I have substituted my formula in that As by, so Fs by As means L0 into B. L0 is T1 by sin phi. So, now sin phi will go up, then Fs into sin phi is divided by T1 into B. Clear, everybody? Understood, guys? This is how you are supposed to calculate your shear strength. All right. Let me give you and some other formula also. merchant's minimum energy criteria. Merchant's minimum energy criteria. Merchant's minimum energy criteria. Merchant's minimum energy criteria. So that is equal to 5 plus 25 plus 1 minute guys. 25 plus beta minus alpha is equal to 90 degrees. This is called merchant's minimum energy criteria. If this relation is satisfied, so that the energy, minimum energy required for proceeding the machining operation is come under, minimum energy criteria. Clear everybody? Right. Next, merchant's constant. Machining constant or merchant constant. Merchant's constant. Merchant constant. That is Cm. Right. Now here Cm I can write it as Cm machining constant is equal to, it is going to be a 25 plus beta minus alpha is a machining constant. Okay. Right. Next is specific cutting energy. Specific cutting energy. Specific cutting energy, that is equal to, we can write it as work done divided by metal removal rate. Work done divided by metal removal rate. Okay. Now work done I can write it as, so Fc into Vc, and divided by metal removal rate is into, so T1 into B into cutting velocity. Okay. So cutting speed, feed, depth of cut is come under this one. Okay. Now, so here I can write it as joule per mm cube. Okay. Right. Now, if I remove this, Vc will get cancelled now. So that Fc is divided by T1 into B, such that I am going to get units is here Newton per mm square. Yes guys, Newton per mm square I am going to get my this one. Okay. Right. So now this is all about so cutting velocity, merchant circle analysis. So if you practice this, so that you are going to get more number of problems in it. Okay. So right, this is all about part 2 session guys. All the best for your exam, and do well in your exam, practice formulas and do well. Okay. Thank you all.